pH, and their clusters. He has also guided several doctoral theses in the field of chemistry and has been involved in several research projects, including those funded by the Indo-French Center for Promotion of Advanced Research and the Department of Science and Technology. Today, he will be sharing his expertise on the application of shock waves in chemical kinematics. Please join me in welcoming Professor Arvind to the podium.
Thank you.
Good afternoon, everyone. Can you all hear me?
Yes, sir.
Okay, this is working as well. I hope all of you finished lunch now. It's time to take a nap. So let's see. So I'm going to talk to you about chemical kinetic studies using a shock tube. I'm a physical chemist, and my main interest is in doing chemistry. But I hope I can convince you how shock tubes can be used to do this. That will be the focus of my talk. This is a brief outline. First, talk about chemical kinetics. All of you have had a course on chemical kinetics now or not? In +2, I won't use any equations that you may not know. So let me just use the equations you studied in maybe +2 chemistry. I will talk about vibrations. How many of you heard about vibrations? Of course, vibration has many meaning. Mechanical engineers would of course be using it. If you have to build a building that won't shatter during an earthquake, you have to ensure that the vibration in the earth is not coupled to the building. Of course, we study the molecular vibrations. We'll spend some time on reaction coordinate and talk about some reactions, and finally talk about some ignition delay. Of course, as aerospace engineers, I'm sure all of you worry about propulsion of rockets and so on. Invariably, you'll have to use some fuels and they have to burn at some rate, and that's what we can do. But before I talk about all of them, let me just see the picture of two of the scientists from India. How many of you are aware of Meghnad Saha? Of course. So Saha is not very well known. Was an Indian astrophysicist. This equation is called Saha equation. If you remember the Maxwell-Boltzmann distribution, you can see something similar. It's always an exponential energy by kT. In fact, he founded the National Academy of Sciences. It's called Indian National Science Academy now. In fact, he also drafted the science policy for independent India before India became independent. Because he was nominated for the Nobel Prize, but he didn't win it. He was also active in politics. He became an MP. It's okay, that's better, yeah. Of course, all of you know C.V. Raman. We had the Science Day just recently, last week, 20th of February. He was born on 7th November. He developed a technique that's used extensively now. If you all learned about Raman spectroscopy, how many of you heard about Raman scattering or Raman spectroscopy? Of course, all of you would have heard about it certainly. In fact, this is a Raman spectrum. What's really interesting is that we can use waves. See, measuring the temperature is not easy unless you work from 0 to 100 degrees Celsius, then you can have a thermometer and measure it. The temperature is 3000 Kelvin, 4000 Kelvin. There are no thermometers. And of course, spectroscopy can help. I'm just going to show you some general data. This is the solar radiation that we measure on Earth. All of you know the VIBGYOR, isn't it? We see visible light from sun, but it also has ultraviolet 400 to 700 nanometers. This is in micrometer. Here, this is the visible range. Then we also have ultraviolet and infrared light. What's interesting about this is that this could be fitted to 5800 Kelvin block body radiation. So now we know the temperature of the sun. We don't have to go to the sun. We can just measure the radiation and get an estimate about the temperature of the sun. What's interesting is this dashed line is the black body radiation at 5100 Kelvin. How many of you heard about black body radiation? All of you are aware of it, isn't it? That's the origin of quantum mechanics. Classical mechanics was not able to explain the black body radiation. So Planck had to introduce this equation E equal to h nu, and now we can measure the temperature of sun just sitting in earth. But if we come to the sea level, then we see that at various wavelengths, the intensity reaching earth is much less than what the sun emits. And of course, this is how we figured out ozone is there in the stratosphere. And it is actually absorbing the radiation below 300 nanometer. You can see only very little of 300 nanometer reaches earth when the sun emits so high. That's what's in a way saving us, because the UV radiation is not good. But all of this we can figure out just by like, this is something many of you may not have seen. This is the radiation emitted by earth. Like sun, earth also emits radiation, but earth is at 300 Kelvin, so it's very similar to a black body at 294 Kelvin. How can we measure this? Of course, you have to go out of earth and have a detector pointing towards the earth and measure the intensity at this wave number. This is the infrared region of light. The reason I am showing you infrared region is that's where the vibrations of molecule occur, and they are important for the reactions to happen. And all the reactions will have some Mark-Wise energy. All of you are familiar with the Arrhenius equation, isn't it? That's there in the +2 itself. That's very important because that's what we use in studying shock tube kinetics. The shock tube, we can produce different temperatures and measure the reaction rates, and so we can use Arrhenius expression. What's interesting about this curve is that, so this is 294 Kelvin black body radiation, very close to the earth emission, except around the 700 wave number, you see a huge dip. This is what you would have learned as greenhouse effect. All of you are familiar with the greenhouse effect, isn't it? Earth is emitting radiation and carbon dioxide is trapping it. And that's why we say now we have a global warming. Of course, carbon dioxide has been on Earth after Ice Age. And because of carbon dioxide only and the greenhouse effect, the temperature of Earth was like +30 degrees Celsius or close to 300 Kelvin, and life evolved. If carbon dioxide was not there at all, then it would be an ice age. So the greenhouse effect was important, except now we have added more and more carbon dioxide. We are worried that the temperature may rise by more than 2 degrees Celsius. Now, what is absorbing this It's almost like 700 wave numbers, which is peaking. That's where carbon dioxide absorbs. If we looked at the previous one, 300 nanometer is where ozone absorbs, and the radiation reaching Earth is removed by ozone. Now, the radiation leaving Earth is trapped by carbon dioxide. Now, if we need to understand how these things happen, of course, these are all simple physical chemistry, spectroscopy, and kinetics are very important. So, what is chemical kinetics? Of course, a branch of physical chemistry concerning with the understanding of rates of chemical reactions. And it's different from thermodynamics, which deals with the direction. It doesn't worry about the rates, it's more from equilibrium. Thermodynamics is like the times arrow, where kinetics is the times clock, how fast or how slow things move. Now, what are the time scales we have? And that can be from the Big Bang to a femtosecond. All of you are familiar with femtoseconds, isn't it? 10 power minus 15. Now we have physics and chemistry researchers worrying about attosecond. Attosecond is 10 power minus 18. So we have changes happening in all time scales. And studying them is the chemical kinetics. Of course, we were wondering about why should I study kinetics at all? Because now it's been removed from the syllabus. For many engineering students probably won't study kinetics. It's very important for what I told you, like ozone depletion and greenhouse effect. But of course, combustion, ignition, propulsion. This is the most important reaction in a flame, H plus O2 giving HO plus O. Your fuel could be cow dung or methane or jet propulsion, like JP10, but invariably, this is the reaction that will control kinetics, the explosion, ignition, because all the fuels will eventually produce hydrogen. And how fast they can react with O2 to produce these two radicals. See, on the left hand side, you have an atom and a stable molecule. On the right hand side, you have two reactive species. So what we call sometimes chain branching, and this is what leads to explosion. Astrochemistry, of course, how many of you have heard about this term? This, how the molecules were formed after Big Bang. And that's, if we study them, that's how we can understand how first DNA was formed and how life evolved. All of them will need. Let me just give you two examples, 2H2 plus O2 giving 2H2O. Is this an elementary reaction or a complex reaction? All of you know the difference between the two? This is a complex reaction. It looks simple, but it doesn't happen the way it is written. We don't have two hydrogen molecules and one oxygen molecules coming and forming two water. It has many steps, but what's interesting is that we can mix H2 and O2 in a cylinder and leave it. Nothing will happen for many years. Even hundreds of years, nothing will happen. But if there's a small spark, this can reduce to microsecond. It can lead to explosion. If you just mix H2 and O2, they will just stay unreactive. You can see the half-life. How many, all of you are familiar with this term half-life, isn't it? Time taken for the reagent to reduce to half of its value. 10 power 25 years. That's larger than the age of universe. It won't react at all. But a small spark can lead to explosion. And if you look at this other reaction, this again, it won't happen this way. CO plus 3H2 giving methane plus H2O. The equilibrium constant is 10 power 400. only one molecule of CO left in the universe. But then it's the second most abundant molecule after H2 now in the universe. It means it doesn't reach equilibrium, that's where kinetics becomes important. It started from a Greek word kinesis, it's movement. In physics and engineering, study of motion, the force acting on the body. Dynamics was the term used in the past, it's been largely replaced. Mechanics is a branch of physics, in relationship with matter, force, and energy. Kinematics is used to describe the branch of mechanics that deals with pure motion without any forces. Of course, in chemical kinetics, we talk about how reactants come together and form a product. As far as chemistry is concerned, I can say kinetic studies how a bond is broken, the bond is formed. Of course, it's a reaction. Because what is reaction? Of course, if you go to a movie and look at this, everybody will be reacting. So there was some cause and then there is some reaction. Chemical reactions also happen because of some such cause. Forces acting on the atoms and molecules, study them. Chemical reaction by definition, chemical substances are transformed from one to another. Say today chemical bonds are broken and formed. The relative positions of atoms and molecules change. Electrons have to move. We only worry about the atoms, so electrons have to move with the atoms. The detailed mechanisms is often called the reaction path or reaction mechanism. So what is the action that causes this reaction? I showed you see your favorite actor and all of you start shouting in the sleep. But what causes a chemical reaction? This is a simple reaction. Is it hydrogen becoming to hydrogen atom? How can H2 molecule become to hydrogen atom? You have two atoms. There is a bond this. You keep, this is called what we call as vibrations. When the distance between the two changes. As you go on increasing the energy, at some point they no longer interact with each other. They become two separate atoms. So in this case, the reaction coordinate is very simple. The distance between the two bonds. This is similar, the distance between two carbon atoms. Butene, how many of you remember? It's 4 carbon. There's a cis and transform depending on where the two methyl radicals are, two methyl groups. How can this reaction happen? Hmm? You're talking about catalysts. I'm just talking, I want you to think about how the atoms move within the molecule and then become products. As in H2, we are talking about the distance between the two atoms changing. In methane, it's the same. But if this transition has to happen, what has to move and how should it move? Hmm? So you have like this, two carbon atom and two hydrogen atom. Now if it has to become cis and trans, one of it has to rotate. Hmm? Now if it's like a methane, C single bond C, this is a C single bond C. This is what we call as a torsion. The barrier for this rotation is small. If you are familiar with substituted thing, we can talk about trans, gauche, eclipsed, and so on. But in a double bond, it's difficult. So you need to break at least one bond, so it doesn't happen. Here also you need to really provide enough energy for the H2 molecule. So here it is actually a rotation about CC bond that leads to the reaction. If I have ethyl chloride becoming ethylene HCl, what would be the reaction coordinate? Here it's just the HH bond, here it's CC bond, here it's about rotation about this bond. HCl going to HNC, Hydrogen has to go from carbon to nitrogen. So if you have seen, basically the hydrogen keeps what we call as a bending mode, hmm, and this amplitude goes on increasing, and eventually it goes to the other side. Here it is bending, here it is rotation, here it is stretching. These are all vibrations. Of course, here it's not trivial to understand it. One carbon, chlorine from another carbon, both have to come together and then form a bond and leave. So this is complicated reaction. This is ethyl chloride structure. This is the product. Chlorine head. Green color here, basically this hydrogen and this chlorine should come together and then break from this. It's not easy to do. Of course, I will just skip this. Rate, there are many different meanings. But in chemistry, we talk about how fast or how slow the reactions happen. In fact, the first time it was done is almost from 1818. Louis Thénard, he discovered hydrogen peroxide and discovered how it decomposes, how it becomes 2OH radicals. Wilhelmy studied the rate of inversion of sucrose. In fact, he did write a differential equation. All of you are familiar with this, isn't it? I will probably mention this. We have a reactant going to product. I can write a kinetic equation. All of you are familiar with this, isn't it? We have a write a differential equation. In fact, it was started by Learn. He was the first to do this. What's even more interesting, he also proposed an empirical equation to express the influence with respect to temperature. Of course, then we can talk about order, molecularity, elementary and complex reactions. All of you have heard about these two terms, order and molecularity? Hmm? Yes or no? Yes. Order is experimental and empirical. Hmm? Molecularity can be defined only if it's an element reaction. When I say element reaction, the reaction happens as it is. 2H2 plus O2 giving 2 water is not an element reaction. If you write a rate equation, the sum of these exponents are, in fact, the order. It's experimental. It can also be non-integer, it can be zero. All are possible. So molecularity is the number of molecules involved in element reactions. You can have unimolecular, bimolecular, or termolecular. Beyond that, it is not possible. As of today, there is no evidence for any reaction in which four molecules come together and react. There is no example at all. Mostly unimolecular, bimolecular, termolecular. Because as I told you, this is not an element reaction. For this reaction to happen, first hydrogen has to break to give hydrogen atoms, and hydrogen atoms will react with O2 to give OH, and OH can react with hydrogen to give water. See here, write many steps. Because this is a typical, if you monitor the concentration of A as a function of time, you will see this kind of an exponential decay. At every point, you can take the slope and get the rate. With this equation, I was telling you about, all of you are familiar with this equation, isn't it? It's called Arrhenius equation. And of course, you can't finish high school without learning this today. It doesn't matter whether you become a doctor or engineer. This you would have learned. And this is the key for the work I am going to talk about. This is an empirical observation. But what's really interesting about Arrhenius is a Swedish scientist. But he was the first to identify global warming. This you may not be familiar with. Arrhenius equation, all of us know. He was the first to mention that greenhouse effect due to carbon dioxide can affect the temperature of Earth. Of course, he estimated it to be about 5 degrees, but eventually it reduced, he had some errors in his calculations. So the net effect was less than what he predicted. So Arrhenius was the first chemist to be getting the Nobel Prize as well. Arrhenius's expression, this one is empirical. All of you know what is meant by empirical, isn't it? There is no basis. We do experiments, we find rate constants, we do it at different temperature. We see that it follows this equation, but it is not from fundamental theory. So in the 20th century, particularly the first 3-4 decades, several theories came. One is collision theory, another is transition state theory. Did you all study this in high school? No. Basically, they try to explain the basis of Arrhenius theory. Collision theory is simple. Basically, it calculates the velocity of different molecules and find out how many collisions can happen per second. This sentence makes sense to all of you? The molecules are moving randomly. If you increase the temperature, the velocity will go up, and you find out how many collisions are there per second. And it assumes that it will be equal to the rate of reaction, as the molecules have to come together to form products. But this assumes that all the collisions will lead to reactions. That need not be true. Transition state theory is much more elegant. It looks at how each of the molecules, each of the atom in a molecule move, how they come together and how they form reactants. Translational, rotational, and vibrational energy. You are all familiar with this? Translation is just motion, like I'm moving now. Rotational motion is like there are 3 possibilities. On vibration, we solve the rest. Any molecule having an atom can move in 3 directions. It can also rotate in 3 different directions. And 3n minus 6 vibrations are there. So you have a reactant and a product. It has to cross a barrier to form product. Arrhenius basically came up with this explanation, and that's why it's called Arrhenius equation. The A is called the activation energy. Now, if you have to measure this activation energy, we need to do experiments with shock tubes. So I'm giving you all this long introduction. I showed this again. I take ethyl chloride and heat it in a shock tube and see that it becomes ethylene and HCl. I do it at different temperatures. I can get the rate constant and do this. So before going to that, let's just think about, okay, I think I already showed this. Wantoff suggested this before Arrhenius, but we still call it Arrhenius equation because he came up with this explanation that molecules have to be activated. Now, as I told you, each molecule has 3 degrees of freedom: translational, rotational, and vibration. This is something all of you are familiar with, isn't it? We can move in 3 directions. We have unit vectors I, j, and k, isn't it? So if I have the total translation energy as half mv square, I can write this as px square plus v square plus z square. This is simple. If you watch cricket matches nowadays, they will put the speed of bowlers, isn't it? They'll say 100.2 kilometer per hour or something. The bowler releases the ball, it goes in some trajectory, and then you know the speed instantly. Ball never goes in x direction, y direction, and z direction. The velocity is some arbitrary, but we always write this as x plus y plus z. Now, why do we do that? If you know why we do this, we have 3 components. It's not 2, it's not 4, it's a 3 component. But the reason we do this is that ij and k are orthonormal. You're all familiar with this, right? They are all orthogonal to each other. So if you take the dot product of I and j, it is 0. If we take the dot product of I, it's 1. If we do this, this three-dimensional problem can become three one-dimensional problem. And that's the key. It's a three-dimensional problem. When I deconvolute this into ij and k, it becomes three one-dimensional problem. Similarly, I can do rotation. I'm sure you all learned about rotation somehow, somewhere. We need to worry about the moments of inertia. For translation, we look at the mass. For rotation, we need to look at the moments of inertia. In moments of inertia, about any axis can be defined by this. The problem is when you have three different directions, the moments of inertia need not be the same in the three directions. Mass would be the same, so if I write the kinetic energy, I can just write p square over 2m. For rotation, I cannot do. Easiest way to understand is this pointers, right? If I rotate it this way, it's easy. If I try to rotate it this way, it's somewhat difficult because the masses are far away from the axis. So rotating it, this is one, this is much easier. Now, because of this, rotational motion is always more complicated, but we don't need to worry about it. Basically, what we have is three rotations ABC, three translation x, y, and z. If we remove them, there are 3n minus 6 or 3n minus 5 vibrations. For a diatomic molecule, there is only one vibration, because 3n minus 5. And that's what we normally, for the potential energy as a function of this, you go on stretching it, at some point it becomes two hydrogen atom. If you go to polyatomic molecules like water and carbon dioxide, they will have 3 or 4 vibrations and they are shown here. It's important to understand the vibrations. Let me show you. So this is, we call as a symmetric stretching, isn't it? This is asymmetric stretching. One bond becomes short, one bond becomes long. These are two different bending modes. In fact, it is this bending modes that cause global warming. This is like 700 wave number. It coincides exactly with the radiation emitted by Earth. Anyway, we already talked about this. I had given you this examples. Now I take you to a big molecule like CS2B or CS2OH. It will have 18 vibrations. And these are 6 of them. Have you all seen this before? Of course, it looks complicated, isn't it? But it's very simple. They'll tell you it's like IJK for vibration. Basically, each of this mode is normalized. If I write the vector about this and take the dot product with the vector of this, it will be 0. And each of them are normalized and all of them are orthogonal. See, for translation, it's easy to find out the 3 directions. For rotations, we have 3 directions. The 3n minus 6 is vibration, and there are many of them. And the reaction coordinate that you may have seen is basically one such vibration, which takes the molecule from the reactant geometry to product geometry. Yeah.
So the excitation needed for vibration, is it always in vibration or is it only during a reaction?
The reaction coordinate is vibration. But what it is not very well taught in many places. So I'm trying to spend it. You have to understand this is a vibration. See, the main thing is that even though there are 6, as you can see, in all the vibrations, almost all the atoms are moving. I can put an arrow on each one of them to show You can see oxygen is moving little bit, hydrogen is moving more. Hmm. This is because of what we call as a reduced mass. If you have hydrogen vibrating, they will have equal amplitude, H2 molecule. But if you have OH vibrating, hydrogen will move more, oxygen will move less. Now, anytime you see a diagram like this, these are common in all the books, it may be there in +2 also. No one explains what this reaction coordinate is. It's basically the distances, angles, diagonal angles, all of them of many of the atoms changing. Hmm. For example, if I go to this geometry and find out all the vibrations, I will find many vibrations and one, if we can all see here, the carbon hydrogen bond is almost breaking, hydrogen is moving towards the bromine. Hmm. And that's what happens at this point. Once they move to this side, HBr is formed. They come to this side, it is the reactant. I just want to remind all of you about some things that I'm sure you've learned. All of you are familiar with this diagram, isn't it? Potential energy curve. Hooke's law, all studied, isn't it? V equal to half kx square. Hmm? What is k in this Hooke's law? Plasticity or force constant. Force constant is familiar to all of you? Young's models. Know how the engineers learned this. So basically, this is the potential energy, and this is the some coordinate. Hmm? And what is force? Minus del V by del X. Is this familiar to all of you? Hmm? Hope some of you have studied. Basically, what it tells you is that when the two atoms have a distance really long, there is no force acting on them. The slope is zero. Hmm? As they come here, now of course you see that the slope goes on increasing. This is attractive force. Here the force is again zero. This side you have repulsion. This attraction. Now if we look at this point, here it's a minimum, here it's a maximum. Here there is no restoring force at all. As long as the atoms are within this region, they go on vibrating like this. When they come here, they go from this side to that side, it's gone forever. It becomes a product. And that's why we call it a reaction coordinate. And transit state theory, basically what it was telling us this, irrespective of how you heat the molecule, this is all vibration, you take it step by step, or use a photon, put a lot of energy, or combine two radicals. All of them could be explained by assuming this transit state theory and assuming that the energy flows. But it turned out there are these two molecules for which there was a controversy. For this molecule, the way you energize didn't matter. You are always seeing this reaction. Whether you are heating it or photoactivation, chemical activation, anything you do, it was similar. But for this molecule, it was very different. So this was a big controversy, and I joined IASC. This molecule eliminated HCl. This molecule they thought was CCl bond was breaking. There's a lot of papers published on this, but this did not make sense. So does it violate transit state theories? One thing about shock tube, I think you already heard a few talks on shock tubes, isn't it? All of you understand what's a shock tube. We produce a shock wave, it compresses the molecules, temperature and pressure both rise. The shock tube itself remains at room temperature. This is something many don't realize. If I want some reactions to happen, all of you are using a microwave oven, isn't it? What's the difference between microwave oven and a regular oven?
One uses convection, the other one uses
Microwave. Hmm? Vibrations, rotations. Basically, in the microwave oven, water absorbs microwave and gets heated. Hmm? So you cannot put any material, you need microwavable containers. And if the food doesn't have water, it will not heat. But almost all the food have heat. But if you look at a furnace or different ovens, wall gets heated up first. And then the molecules collide with wall and they get heated. The shock tube wall remains at room temperature, but the molecules get heated. So that was a very good way of testing the transit state theory. But some work were done in the furnace, so there was some controversy. So this again A and EA, activation energy and pre-exponential factor. These are HCl elimination from different reactants. We show you a table like this, of course, you'll be wondering what it is, but I'm sure all of you can see that there is something wrong with this particular row. It lists the activation energy and pre-exponential factor for many different substitutions, but you see that there is something wrong with this row. It doesn't look like anything else. But if you make a plot of this log K versus some parameter that's given here, that really fits the line. This was the controversy we had, so I thought we need a shock tube. I think many of you have met Professor Reddy, who was here yesterday. So he had a shock tube, so we wanted to use this. So we can heat the molecules in millisecond, microsecond time scale and raise the temperature. And we do the reaction and we collect the products. This is a shock tube we built many years ago. I won't give you the detail. This is just the schematic diagram. So this is what we call as a high temperature pulse. The primary shock raises the temperature here. The reflected shock raises it further. And then an expansion fan cools it down really fast. So what we can do is to raise the temperature of the molecules to any level and keep it constant for about a millisecond and suddenly cool it. The shock tube remains at room temperature, but the molecules have been heated to great temperature. These are just some explanations, but let's just skip all of them. It takes a lot of time and effort to understand how it works and do the what. So we did do that, and finally, as you can see, depending on the different parameters in the shock tube, we can get longer reaction time, shorter reaction time, or you can even have a pressure trace like this when temperature and pressure are changing continuously. This won't be of any use at all. We need to produce constant temperature and pressure, and that we can do if we understand how the shock tube works. Because we did do a lot of experiments and theory to understand all of them. We skip that. We can also use some standards to get the actual temperature. So we produce temperatures from 1000 to 1200 Kelvin, as you can see, and then collect the spectrum of the products. This is hydrogen chloride, which absorbs around this. So we saw that this molecule breaks into HCl and vinyl chloride, and we could get the rate constant accurately. And then if we put it in the same table, now we see that they are very similar to all the other ones. So if we build a shock tube and do the experiments carefully, you can get kinetic parameters that are reasonable, then that will they will agree. In fact, there were like 40, 50 years this was a confusion. Nobody knew why this was somewhat different. And of course, this is of interest only to physical chemists like me. Many may not worry about why they are different. But once we build a shock tube, we can do many things. Because we could eventually explain this, but maybe I would. Yes, we can calculate all this by finding out how the transition state looks and what is the reaction coordinate. I can calculate this with computational chemistry and really get all these parameters. This is not working. It's very similar. The CH bond will break. It will form a HCl. And this we can also do the experiment and also theory. Now we have complete understanding of this. But this is the reason we did do the shock tube. We built the shock tube and we are doing all these studies. But once we build it, we can do a lot more things. We found out that if we increase the activation energy and also pre-exponential factors, the rate constants may be very similar. This will lead to some confusion. The literature had a lot of this confusion. If A and EA both increase, the rate constant will be somewhat similar. But this is very important for the engineers to understand because they will take parameters like this from the literature and use them. Now, if we have a molecule like this, there will be many different possibilities and you can have many, many products. And let me just show you. Okay, I think this is all not it. I was telling you about the global warming and ozone depletion, isn't it? How many of you are, I'm sure all of you have refrigerators at home, isn't it? We are using CFC before, chlorofluorocarbon. Now all the refrigerators will be claiming to be CFC free. There will be a label. In fact, this is again a lot of kinetics and photochemistry. Now chlorofluorocarbon goes up in the atmosphere. It's dissociated to producing chlorine atom, and chlorine atom reacts with ozone, which led to the ozone depletion. The chemist understood this. All they had to do is to first add a hydrogen atom, because when you add a hydrogen atom to the molecule, the lifetime reduces. OH radicals will react with this. If you don't have a hydrogen atom, it's very large. If you add a hydrogen atom, the ozone depletion potential reduces dramatically. So most of the chlorofluorocarbon replacements were like this, adding only a hydrogen atom. So you can see ozone depletion potential could be almost made to zero. But then that's not the only problem. We have global warming. Carbon dioxide is like one. These hydrofluorocarbons, which are good as CFC replacement, had much higher global warming potential. So we need to worry about this. And finally, fluoroethanol was suggested to be a CFC replacement, which also had low global warming potential. So we studied this molecule, but this is a lot more complicated. There are many, many reactions. This is what we call as a complex reaction. So we need to collect all the products and come up with a mechanism. So we use 26 species and 55 element reactions. Then that led to a detailed reaction mechanism. We can look at each of the products and reactants. We can use GC to collect them and also use the reaction mechanism to predict them. This takes a lot of time and effort, because here it's working. You can see these are two different reaction coordinates. In this one, you have water being formed with vinyl fluid eliminated. Here you have HF being formed with vinyl alcohol. So all of these are different vibrational motions, and that we can now completely understand. And of course, we can calculate the A and DA for all these different products. And of course, we just calculated them and published them. Ethylene can be formed by many different reactions and also direct reactions, and we can get the rate constant for each one of them. We also expected a HOF elimination, but the theoretical barrier was very high for this. So there are many other reactions that can give this. Then we looked at the chloroethanol because we had reasons to study them. These are all lots of data. Maybe I will just skip them. Anytime you do this kind of reactions, you will see these tables. There will be hundreds of reactions for each one of them. We can calculate the pre-exponential factor and R2S energy. And to fitting so many reactions with so few parameters, there will always be some uncertainty. We can identify the important reactions. All these reactions were studied by us, and we got the R2S energy and pre-exponential factor. Because we can do modeling and we can predict the concentration by theory as well as experiment. We see that they have very good agreements. So these are all for the different reactants and products. So only for each one of them we can find the transition stage. Each of this reaction is one vibration. Because there are so many vibrations possible for going from this to different products. You can find out each one of them have a different transition state. So this is for one reaction. This you can see for four different reactions, four different transition states. The beauty now is if you look at a shock tube, we'll be wondering how can this give all this data? But we can get this data now because we can measure the reaction rate constants at different temperatures. We can measure them over 1000 Kelvin range, and in order to explain them, we can really prove the reaction is happening this way because the A and DA would depend on how they happen, and that's what shock tube can give us precisely. So told you once we build a shock tube, there are many other things we can do. Even though we built it only for doing some fundamental chemical kinetics work, ISRO and DRDO were asking us to measure ignition delay. Now, what is ignition delay? This is something aerospace engineers will be studying. You mix a fuel and reactant, and how long does it take before it ignites? That can be measured with the shock tube. Remember, I had shown you pressure traces like this. If I just put a fuel and heat it, after some time we cool it, you can study pyrolysis. How the molecule decomposes into different fragments. But if I put a fuel oxygen mixture, after some time, the ignition could happen and the pressure will rise dramatically again. At the same time, we will form CH radicals and they will be in electronically excited state and they can emit. So we can look at CH emission as well as pressure rise and we can measure the ignition delay. Because after we built the shock tube, scientists from ISRO came and asked me if we could do this. Of course, we could do this, so we started doing this. This is called JP10, jet propellant 10. This is a fuel of choice for NASA sometime, and ISRO was also considering this. This is kerosene also, one form of kerosene. The chemical name is tetrahydrodicyclopentadiene, and this is a very unique fuel because it's the only fuel that is single component. For example, if you look at petrol and diesel, there will be many hydrocarbons. There can even be 40, 50, or even 100 hydrocarbons in each fuel. But this fuel is a single component fuel. It has only CC and CH bonds. This has been chosen for scramjet. And we could measure the ignition delay as a function of temperature and find out the R2S energy and so on. In DRDO, they were asking if there any way to reduce the ignition delay of this molecule. Of course, they also suggested triethylamine as an additive. All of you are familiar with amine, isn't it? Methylamine, ethylamine. The only difference is that there is a CN bond. This is the most bond. Will you get that pen?
Yes.
Yeah.
Sir,
Yeah.
so the ignition delay, what is it currently, and what is DRDO looking into get reduced?
So this is one option. Adding an additive. And this is all triethylamine. If we have that JP10 has only CC and CH bonds. This is like 90 kilocal per mole, and this is like 100 kilocalorie per mole. CN bond is typically 70 or less. So if I have or a little bit of triethylamine, this bond can break faster and that will produce ethyl radical. Hmm? And ethyl radical almost immediately reacts to give hydrogen and ethylene. So you would produce hydrogen atom. As already mentioned, this is the most important reaction in combustion. You can immediately have this reaction and then can almost explode or so a little bit of addition of triethylamine can reduce the activation energy and reduce the ignition delay. In fact, we did do the experiments. You can see when you add this, it reduces from 50 or 40 to 30 kilocalorie per mole activation energy. And of course, using this in a real system is not that trivial. Often, when you get a fuel from Russia or America, we won't even know what the components are. And they may say they are using some fuel and they may be adding some additives that we do not know. That's why it's important to do these experiments here. But I had not talked about JP7 and RP1. I don't know if I have the data here, but I'll have it in my laptop. There are like 100 plus hydrocarbons. This is the only one that has a single hydrocarbon. And to measure ignition delay for them are not trivial because you don't even know what it is. Often engineers use what is called a surrogate fuel. It will have properties similar to the actual fuel used in terms of the major microscopic properties. That may be only one or two molecules. And then we end up studying them. Another thing that we did was somewhat unusual. If you look at a missile or rocket, all of them have this kind of a cone at the edge. And drag is a very serious problem. What we showed was in this, we just coat some chromium cone. When the rocket re-enters, that will lead to the evaporation of chromium, and chromium will react with oxygen to give chromium oxide. And this is exothermic. The heat addition can reduce the drag. Of course, we did the experiment and showed that it reduces the drag because we just published one more paper for us, but we didn't realize this was immediately picked up even by Pakistan and America. Because the advantage is that you don't need to come up with a new design. You can use the existing designs and just coating. That could increase the basically the length it can travel if the drag is reduced. Of course, another completely unexpected thing is that we studied shockwave processing of C60. All of you are familiar with C60 now, isn't it? Not C6, but C60. Buckminster fullerene. It's called fullerene. C16. So what we did in this experiment is to take C60, have some hydrogen and expose this to shock wave. Now, why did we do this? In fact, it's the opposite problem of soot. How many of you have studied about soot? Because it's important. So, yes, first half an hour or more, I was just talking about some simple chemistry and theories. But slowly, we'll see the importance and how it happens. What is soot? How many of you know what is soot? Hmm? Carbonaceous particles. Isn't it? So do you know the formula of soot? See, all the other molecules I showed you nice formula and see how these atoms are moving. C60 has only carbon. Soot formula is basically CNH is what sometimes people will put. There is lot of carbon and some hydrogen. If you look at this molecule, all of you know certain benzene. This is C6H6. If we add one more ring, this is C10H8. If I add one more ring, this is C14H10. I can go on adding more and more rings. These are all called PAH, polycyclic aromatic hydrocarbons. Is it three-dimensional or is it a plane? This is two-dimensional, and that's a very important question. As you can see, this is two-dimensional. And that's not soot. Soot is three-dimensional. In fact, chemists, mechanical engineers, everybody was worried about soot formations. How is soot formed was a big question. Because whatever fuel you use, end up with soot. So we have to find out how soot is formed and how it can be reduced. In fact, from University of California, Berkeley, one mechanical engineer proposed that PAH is formed first. And the PAH comes, joins and forms PAH2, 3, 4, and so on. It becomes three-dimensional. And that was really ambiguous. Because this cannot happen, like two benzene cannot form benzene dimer. This is what we call as van der Waals kind of forces. That cannot happen. In fact, I had some French collaborators who are listed here. They wrote to me and said this kind of thing cannot happen. So there will be some other explanation, so we are working on this. But what we have seen here is that you start with the hydrocarbon, you ban it, and eventually end up with soot, which is all carbon and some hydrogen. Now, if you think about the opposite, you had only carbon initially after Big Bang. How are the hydrocarbons formed first? How are the molecules formed after the Big Bang. That's what we wanted to study. So we just took C60 and put some hydrogen, and then we collected all the products. We showed that it was forming methane, ethane, benzene, this thing, and we could study them in detail. So I had chosen a few examples just to tell you, the reason I went to the aerospace lab to build a shock tube was fundamental chemical kinetics for me. But once we built it, now we are doing combustion, ignition, astrophysics. Because the Big Bang is one of the first shock in the world. And then, even today, how was the first amino acid formed? And one of the postulates is that it happened in meteorite impacts. How did the life originate on Earth? One postulate is that asteroids brought the, like comets, amino acids into Earth. And then further impacts made the chemical reactions. If you are all familiar with the Urey-Miller experiment, you have studied about that, isn't it? So what they did was to just take water, methane, carbon dioxide, everything, and just expose them to high energy. But that does not answer one important question. It showed the production of amino acid, but they are not chiral. Chirality, you well heard about it, isn't it? Chirality is essential. Life is chiral. But the Urey-Miller experiment did not produce chiral amino acids. It produced racemic, basically both left and right handed of equal amounts. In fact, now we are doing a lot more work on this line with some French collaborators, where shock tube is used to produce conditions that are somewhat comparable to what is found in space. So once you have a technique which is built, the uses are enormous. How many of you understood the two tables I showed you? One row was clearly wrong. So that's why we built the shock tube. We did the experiment and showed that there is no problem with it. But once you hit the shock tube, instead of just putting a molecule, you put a molecule and oxygen, you can produce ignition. You can put just carbon and hydrogen, you can produce hydrocarbons. You can also take the hydrocarbons and do just the pyrolysis and combustion and look at soot formation. So all these are being done using shock tubes by physical chemists like me. And often in this field, you will see engineers becoming chemists and chemists becoming engineers based on need as you go on studying more and more. I think I'll probably stop here now, but I'll be happy to answer any questions any of you have about any of this topic. I will try to answer to the best of them. Yeah.
You mentioned about computational chemistry.
Yeah.
I'm just wondering how good are these models to describe reality?
Actually, I can give you an honest answer because I'm not a computational chemist, so I won't be offended if I say it's improved dramatically, beyond my imagination. If you are like a BSc student taking quantum chemistry course or quantum physics, they will say there are only four exactly solvable model: hydrogen atom, rigid rotor, harmonic oscillator. But you have come a long way, particularly for hydrocarbons. For example, I can calculate the enthalpy of formation to within a kilojoule per mole. any hydrocarbon. The techniques have really improved. So in fact, we have a paper on combustion and flame just being answered. We can calculate them very accurately. In fact, the first paper we published, we showed that the experiment and theory don't agree. Mhm. And the referees were very appreciative because you don't find anything wrong with either the experiment or theory, but they don't agree in terms of the techniques used and analysis. And eventually it kept improving. Now we know a lot more. So they have become enormously powerful.
Any questions?
So how did they first discover these stretching, bending, and torsion modes?
Actually, it is, in a way, this is all predates physics and chemistry. Engineers have solved this problem, harmonic analysis. So that is old. Hmm. That's why I was spending some time. These are like three orthogonal vectors for translation. Hmm. Basically, when you have 3n minus 6 modes, you basically have three vectors on each atoms. This is 3n vectors. So you find linear combinations of these 9 vectors that will be orthogonal to each other and normalized. That's how we find the stretching, bending, torsion, all of them. So understanding them from first principles is easy, it's not complicated. It's clear. Finding the linear combinations of these 9 so that all of them are orthogonal to each other, individually they are normalized. And of course, for a molecule like water, it's easy to show that you get a symmetric stretching, asymmetric stretching, and bending. But if you have fluoroethanol, like the 18 vibrations, or benzene will have 30. But the maths is now easy. You can calculate them. You can also find them experimentally. We can see which of the modes will be active, which of the modes are not active, and use infrared spectroscopy to find it.
So, instantly changing the temperature within the shock tube system,
Yeah.
doesn't that affect the reaction in other ways?
See, the instant is one word, isn't it? What does it mean? What does immediate mean? See, it's a very important question. In the shock tube, I had shown you normally the primary shock rises the temperature a little bit, the reflected shock, and then it goes like this. If you noted this time scale, this is like 1 millisecond typically. Hmm? And the cooling takes place for 1 or 2 milliseconds. But this rise time, it's instant here in this graph because each division is like 500 microseconds. If we expand the scale, it's typically 1 microsecond or less. Hmm. And that's lot of time, not an instant. If we compare it with the vibrational period and rotational period. So all of you read about Chandrayaan finding water in moon, isn't it? How did it find water in moon?
Bombarded against the surface and
No.
Water has a certain radiation which light passes through it, reflects on.
See, it's basically infrared spectroscopy. Hmm. Water has the vibrations that we're talking about, symmetric stretch, asymmetric stretch. Hmm. It absorbs around 3,600 wave number. And they found this. Now 3600 wave number, all of you are familiar with this unit, isn't it? Hmm? Wave number c times nu bar is nu. C is the speed of light. Hmm? So that is 3 times 10 power 10 centimeter per second. Let's say it's 3000 wave number, or let's say 3300. So that is like 1 times 10 power 14 hertz. If you look at the overhead stretching vibration, that is 10 power 14 hertz. If we convert this to time, this is 10 femtosecond. Vibrational period is like femtosecond to picosecond. So all the vibrations happen. If you have enough time for a few vibrations, the reaction will happen. So microsecond is a very long time compared to this period. In fact, in picosecond, nanosecond, there will be complete equilibrium, thermal equilibrium. Rotational, translational, vibrational, all the energy would be thermalized. So microsecond is a very long time. But that's the advantage of shock tube. But now there are some who do lasers and look at time scales of even femtosecond. So shock tube that way has the ideal. This is all completed. So it's a thermal equilibrium.
So how can be the distribution profile of the shock wave in any media?
See you need to know the heat capacity of the medium. But the shock velocity will depend on the gamma. Hmm? So mostly we have argon. If we have to do it through, I'm suppose Jagadish may have talked about underwater shock. The shock goes through water or solid, then of course the heat capacity and gamma are different. Mhm. So you won't get the temperatures that I talked about if it propagates through as liquid or solid. But these are being studied. The medium is important, and if we have a mixed medium like aerosol or liquid, then it's a lot more complicated. For those things, the theory are not well developed yet. Complex media.
If anyone doesn't have any questions,
Sir, the ignition delay, what are the condition maintained? Because every scram engine is
Certainly, that's a very important point. The temperature and pressure that we have. Ideally, we should do the experiments in which the scramjet would be operated. So typically, Surya would know better. They have about an atmosphere or less,
Very low density.
and density is less. So we have to do the experiments under those conditions. And then the fuel, actual fuel that's being used. But recently, I thought DRDO has chosen ethylene for the recent test, hypersonic test. So, because there are several labs that do this.
But ISRO uses kerosene.
Kerosene, yeah. So DRDO chose ethylene. That's why we do experiments with. Sometimes we just take the fuel from them. But ISRO gave this RP1. I don't know if you've seen this. It's hundreds of hydrocarbons. In this.
They use the for the scramjets. They use the kerosene.
Yeah. But the scramjet itself, DRDO chose to use ethylene.
a round of applause for Sir Einstein. Over to you.
Thank you so much, sir. I would like to invite our chairman, Dr. Marcel, to participate. I also request all the faculty
All respect for policy.